now we're looking at fractions, because it's talking about denominators here. Remember, in a fraction, the top value is the numerator, the bottom one is the denominator. We're only focused on the denominator. That's it. I don't care what the numerator looks like. It could look really big. It could look complicated. I don't care what the numerator looks like. All I care about is that denominator, okay? And here's why. Because if you look at fractions, and we've seen this, if not here, then hopefully maybe in some other math class, if you ever see a denominator that's 0, what we end up with is something that's undefined. Maybe I should give myself more space. Let's see if we can fit this. Undefined. It's undefined, okay? Now, undefined values, we can't say that those are part of the domain, which is why in the past when we've seen them on our inequalities, we don't actually include them with, we never include those with square brackets. And when we say undefined, we're talking about infinity, okay? And so, I don't know, I kind of feel compelled to say why it's undefined, why it's infinity, okay? Let's take 1. Okay, how much of nothing is in 1? Now, some people would say, just without thinking about this, there's only 1 in 1. That's true, but how much of nothing is in 1? See, well, there's 1 of nothing. Okay, that's true. How about a gazillion nothings? Would that satisfy 1? No. So you see how this goes pretty quickly up to infinity when you divide by 0. Okay, so, you know, there's that picture of some kind of gaping hole in a house when you divide by 0 or something like that. Whatever. It's just saying that it's undefined. Mathematically, we can't quantify how much of nothing is in something. Okay. So, you know, if you want to speculate about that, that's fine. So, now we have to be able to skip these numbers. Okay, so let me, I can't skip the part right there, okay? So in your denominators, you're going to end up with more of these expressions, right? Maybe it's something like x squared minus 1. Okay, all we know is that whatever the x value is, it just can't make that full denominator equal to 0. So whatever it is, what we do is we say we're going to look at it equaling 0, but it just can't equal 0. And so that's why you put the slash sign through the equal sign. Okay, it's just not equal to 0. And again, whatever's in the numerator here, I don't care what's there. I'm only focused on the denominator. Now, some students are like, well, what if there's x's in the numerator? I don't care. I don't care what's in the numerator. I don't care what it looks like. All I care about is the denominator. And then you can break this up and say you're going to figure this out. We solve these pretty much like we would an equation, but again, it's just that it's a not equals. What this does is it tells us values of x that would make the denominator 0, which then would not be included. They would not be included in the domain. All right? I know this one, I don't know that we're going to see anything like this. We could. But we already know how to solve these types, okay? In any case, I don't expect that we're going to see any squared x's. But again, the idea when we put these into interval notation is we have to be able to skip the values that would make the denominator 0. Again, if we're just looking at replacing the x with 0 in the denominator, to make its full value 0, we have to be able to skip those x values. I feel like I'm talking in circles here. So let's look at an example. Hopefully this will help, okay? So I got g of x equals 16 over x minus 15. Now, as I stated before, we don't care about that 16. And you may think that's insensitive, but I'm a math person, so I don't care. Okay, so maybe that's insensitive. But in any case, x minus 15, again, we want to look at when it equals 0, but I'm going to put a slash for that. And I think my slash goes the other direction, but I don't care because it's just a slash, okay? I'm just saying that it's not equal to 0. I just want to know when x minus 15, I want to make sure it does not equal 0, right? So to solve this, I'd say let's go and add 15 on both sides. Okay, now if this happens, I get that zeroed out, I drop my x, now it does not equal 15. Okay, so as long as x does not equal 15, then I can get a true statement out of this, some kind of real number out of this function, okay? Now that would be kind of what we would call the inequality here, but we don't want the inequality, we want the interval notation. So how do we demonstrate that 15 will not be included in the interval? Well, the graph I think will help. Okay, so let's look at the graph. Okay, so you got positives to the right, negatives to the left. I'm gonna put 15 right in the middle. And then, of course, 16. I think I did this one correct. And then 14, okay? So x cannot equal 15. That means it can't be included. That's an open circle at 15. Well, what does that say about all the other values of x? That means that they're okay. So everything to the left of this 15 and everything to the right of 15 is good. So there's my arrows. So think about what the domain would look like just for the green part of this. And we have to be able to skip that 15. Well, I can see to the left that would go all the way to negative infinity. It's going to stop at 15, which is not included. So there's a closed brackets. And then I will unite this starting again at 15, but it's just not included. And then it will go all the way to infinity. So we get some kind of OR statement in here, a union statement with this interval. But you see that it matches the same number. That's because it's not included in either interval. Okay, this is how you skip just individual numbers with interval notation. Yep, so let me address that here real quick. Let's say that maybe 16 wasn't included. Then you'd have to have an interval from 15 to 16, and then you'd have a second union. Maybe I shouldn't have said that. But that, just so you know in the future, because that will happen, they're gonna give you little intervals like that as well. But this one's good. This one's good. We can stop right there.